Problem number 40, find a potential function for this vector field right here. It doesn't say, the problem doesn't ask you to check to see if this vector field is conservative using the partial derivative check, but let's just go ahead and do that right here. So what we need to do is we need to show the cross partial derivatives equal. So we need the partial derivative. Let me just call this m, n, and p right here. So m is this, n is this, p is this. The partial derivative of n with respect to x needs to equal the partial derivative m with respect to y. So the partial derivative of this respect to x needs to equal the partial derivative of this respect to y. And this would be z is equal to z. That checks. And then we also need the partial derivative of this with respect to x. We need to equal the partial derivative of this with respect to z. Partial derivative of this with respect to x is y plus 2x cosine z. And this is equal to y plus 2x cosine z. That is the partial derivative here, so that checks. And then finally, we need a partial derivative. Let me put it over here. The partial derivative of p with respect to y needs to equal the partial derivative n with respect to z. And what does this do here? Partial derivative of this with respect to y is x. And partial derivative of this with respect to z is x. So that checks. And this vector field is defined on the entire, all of R3, all of three-dimensional space. We don't, that's going to be simply connected. So we know that this is guaranteed to be conservative. We know it's guaranteed to have a potential function. Let's find the potential function. So how do we find potential functions? F of x, y, little f of x, y, z. Well, we can find it by integrating the first slot here, m. And we're going to integrate this with respect to x. And when we integrate this with respect to x, we end up with antiderivative of this with respect to x is x, y, z. Antiderivative of this with respect to x would be x squared times sine of z. And then we have to tack on something extra. In Calc 1, we tack on a constant. Here, we don't tack on a constant, we tack on a function that depends potentially on y and z, but not on x. Okay, so now that's one integration, one antiderivative we found. Now we have to find antiderivative of the second slot n. And we integrate with respect to y now. Antiderivative of this would be x, y, z. Antiderivative of this would be y cubed. And then we tack on now a function that does not depend on y, but could depend on x and z. Because remember, we take the partial derivative of this with respect to y, it would be 0. Okay, finally, we integrate this last slot, p xy plus x squared cosine z. Integrate this with respect to z. We end up with xyz plus x squared sine z plus some function that potentially depends on x and y. Okay, so what is our final answer here? Let's combine things. We see an xyz in every term. We see an x squared sine z in those two terms. And x squared sine z could be part of the C2 of x comma z. And then finally, we have a y cubed. And the y cubed could appear in there. And so here is a potential function. If you want to write down all potential functions, what you would need to do is to tack on a plus c where that is an actual constant. That doesn't depend on x, y, or z. But here's our most general form of potential functions. If the problem is just asking you to find a potential function, it's fine to just set c is equal to 0.